Hello guys, what's up? I'm Mohammad Fouad, back with another video about programming. Today's video is the 6th video of our machine learning course. So far, we talked about different types of machine learning. We learned about the cost function. We talked about the gradient descent algorithm, and we talked about gradient descent for multiple features. And today, I'm gonna show a couple of tricks that we can use to speed up gradient descent algorithm and basically to debug it. Today, we'll talk about feature scaling and normalization, and we'll talk about how we have to choose our learning rate alpha for our gradient descent algorithm. So, if you haven't already, go ahead and hit the subscribe button because it helps me out a lot. And without further ado, let's dive right into it. Alright guys, so as I said, gradient descent algorithm is not perfect. Sometimes it can head over to some problems and sometimes it can be really slow. So we are gonna learn 3 ways to speed up things and to prevent some of the bugs from happening. So let's see what are they. Alright, so the 3 things that can help the gradient descent algorithm to work properly and not get stuck in some problems are called feature scaling, that I'm gonna write as FS. Then we have mean normalization algorithm, which I'm gonna write as MN. And the other one is basically to see if our gradient descent algorithm is working and if our learning rate alpha is a good learning rate and if our cost function is decreasing over time. So I'm just gonna write alpha for that, and we'll learn how we can see if our cost function, if our alpha learning rate is a good learning rate and our cost function is basically decreasing, because that's the whole point of gradient descent algorithm. Alright, so now let's talk about what feature scaling is trying to solve in gradient descent problems. Well, the problem is that the graph that the cost function makes against the theta values can sometimes be really wide or really narrow, and that can cause the gradient descent algorithm to get stuck, bounce around, or like become really slow and take a really long time to get into the global optimum point. Let me explain you how this problem can happen. First of all, you must understand that in most of the problems we are dealing with a 3D graph. Sometimes it's like 4D or 5D. I cannot show that to you obviously, but let's say we are working with this graph over here. If you search gradient descent 3D graph on Google, you'll see these kind of graphs. And as you can see, the graph that we have over here is dealing with theta 0 and theta 1, which means that we have 2 features, and this axis over here is the cost value. So what we try to do with gradient descent algorithm is that we try to get to this really low point in the 3D like parabolic shape. We try to find the lowest point so that we have the best combination of theta 0, theta 1, and all the thetas, so that we get the lowest cost function value, which means that our hypothesis function fits the data really well. So as you can see, we're trying to do that. The problem is that gradient descent algorithm works as best if the graph that it's dealing with is a really nice parabolic shape and it's round. Sometimes the graph gets really narrow or really wide because of the different range of different features in our graph. Let me tell you an example for you that you'll see this problem in. Let's say we are trying to train a model that is basically trying to predict the value of a house based on how big the house is, so the area of the house and how many rooms the house has. So this problem that I talked about will look like this. We will have the area of the house on this axis over here, and the area can be from 0 all the way to, let's say, 500 meters squared. And the number of the house, the number of the rooms in the house are in this axis over here, and it can be from 0 all the way to, let's say, 4. And the value of the house starts from here all the way to here. Now as you can see, one of the axes is really long because it starts from 0 and it goes all the way to 500. But the other one is really short and it starts from 0 and it goes only to 4. Now the problem that this will make for us is when we are trying to run the gradient descent algorithm on the graph of the cost function against the theta values. Now if we try to imagine that graph and put the number of rooms in front of us and then the area of the house on the other axis, the shape is going to be really narrow like this. So if I want to draw like a 2D version of that graph just from one side, it's going to look like this. it's gonna look like this. And if we try to run the gradient descent algorithm on this, the chances are it's gonna bounce around like this and never get to the local or the global optimum point, which is over here, which is the one that we are trying to get into using the gradient descent algorithm. Looking at it from the other side, meaning that we put the area of the house feature in front of us, the graph is gonna look like this. As you can see, this graph over here is not really bad for the gradient descent algorithm to work on, but the problem that we have is that it's a 3D graph. And that means that the gradient descent algorithm might work good in this direction, but it might work really bad on the other direction, and it might bounce around and never get to the local optimum point or the global optimum point. So feature scaling tries to solve that. Now the way that it works is pretty smart. It tries to make the range of every feature the same, and the way that it does it is like this. We divide the input feature by the range of that special input. So let's talk about the problem that I talked about earlier, the area of the house and the number of rooms. So it will try and divide each of our input features by the range of that special input. So if we have a training example that says the area of the house of 100 and having 2 rooms is gonna have a value of, I don't know, £1,000. What we try to do is that we divide this 100 by the range of it, and we divide this 2 by the range of it as well. As I said earlier, the range of the number of rooms is going to be equal to 0 to 4, so 4 rooms in total. So we're going to divide that by 4. And the area of the house is going to vary from 0 all the way to 500, so a range of 500. So we divide that by 500 as well. Now, as you can see, no matter what our input feature is, it's going to be always from 0 all the way to 1. So it's going to be always from 0 to 1. And that means that if we try to draw the 3D graph of the cost value against the theta values, it's going to be a really nice parabolic shape. And if you're curious, the formula for feature scaling looks like this. We have the x feature, the ith one, divided by the total range of that special input. Now remember that when we try to predict a situation that we don't have the answer for, we again have to use feature scaling because it's just not gonna work. Now mean normalization algorithm is basically trying to help with the same problem, but it does it in another way. It subtracts the input feature by the mean of that special input. So let's say we have a data set for our problem that I talked about earlier, the value of the house, and let's say the data set looks like this. We have a house that is 100 meters squared, it has 2 rooms, and its value is £1,000. The other house, which is in our data set, has a 200 meters squared area, 3 rooms, and it's worth, let's say, £1,800. So in real world examples, we have many more data examples or training examples in our data set. But here I'm just using 2 to make it simpler. One more point, we use the feature scaling and the mean normalization algorithm for all of our input features. So if I want to use it for one of them, I have to use it for the other one as well. So let's say we want to use this mean normalization algorithm. By the way, the formula for it is like this. Okay, this is how it looks. So let's try and do mean normalization algorithm for the first input feature x0, x1. As I said, x0 is equal to 1 always, and we use it for other things. So let's do it for it. First, we have to take the mean, and as you can see, the mean is going to be equal to 100 plus 200 divided by 2, which is equal to 150. Then when we try to plot this first training example in our data set, we subtract the x1 from the mean. So it's going to be equal to 150 minus 100, which is equal to 50. So we use 50 instead of 100. And it's same thing for the number of rooms. We have 2 and 3, so a mean value of 2.5. And when we try to, let's say when we try to plot this example over here, it's going to be 2.5 minus 2, which is equal to 0.5. So we use this value to plot it in our graph. But the cherry on top of the cake is when we combine the feature scaling algorithm with the mean normalization algorithm, so that we get a really good graph for our gradient descent to work on. So when we combine feature scaling and mean normalization, it's gonna look like this. We're gonna say xif is equal to xif minus the mean for it divided by the range of that input feature. Now this algorithm over here, this formula, is gonna make a really nice graph for our gradient descent to work on. Alright guys, so now let's talk about the learning rate alpha. We know that in gradient descent algorithm, the only thing that is concerning is the learning rate alpha. If we choose a small learning rate, the gradient descent algorithm will be really slow. But if we choose a big one, it might bounce around and skip the global optimum point. So we have to find the sweet spot of the learning rate alpha. Now, how do we monitor our learning rate alpha and see if it's working? So what we can do is that we can plot the graph of cost value against the number of iterations, and the graph should look like this. So we will have the j of theta over here and the number of iterations over here. So I'm just gonna write ITR for the number of iterations. So the graph should look like this. It should start from a high value and slowly decrease as we go and do the gradient descent algorithm, and eventually should plot out and be a straight line. Now if it doesn't look like this and it looks like something like this, or it starts from a high value and it goes even higher, it means that your alpha learning rate is too high. So what you can try to do is you can choose a smaller learning rate and look for this graph and look for this nice curve that I talked about earlier. You should start from this high value and go down eventually. Now we might have another problem, meaning that our learning rate alpha will be really small. Now in that case, we can understand if our learning rate alpha is too small by looking at how many iterations it took. If it took a lot of iteration and we are still in a high cost values, so like let's say the graph looks like this, we know that we are using a really small learning rate alpha. So we can make that higher and make it bigger, so it goes and make this a nice curve in this graph. Alright, so that was it. I hope you learned a couple of things about gradient descent algorithm and how we can use these to basically implement this algorithm in real world examples and problems. If you've enjoyed, hit the like button. If you have any problem, comment down below. I'll try my best to answer to most of them, and subscribe if you haven't already. I have a bunch of videos that I've made already about gradient descent algorithm, about linear regression and the cost function. So if you don't know about them, you can go ahead and watch them and learn. So thanks for watching and have a nice day.